Aloha, and welcome to this special edition of Live from NOIRLab. My name is Jamaica Marshall, and I am a NOIRLab outreach assistant at the International Gemini Observatory, which is a program of NSF's NOIRLab. Joining me today in our virtual studio as technical director and moderator, my colleague, Robert Sparks. He'll be moderating the Facebook live chat, and I'll be moderating the YouTube chat. So please feel free to post your comments and questions anytime throughout today's show, and we will relay those to our guest. Also joining us for this special edition is our colleague from Chile, Manuel Paredes, who earlier today hosted the Spanish version of this show. Manuel, would you like to address our US audience?
Hello, Jamaica. Hello, everyone. Thanks for inviting me to this special edition of NOIRLab, of Live from NOIRLab, sorry. I'm very happy, and we are very happy. We have a similar session in Spanish a few hours ago from our Spanish channels in NOIRLab. It was very interesting, very interesting. We got a scientist, a very important scientist related to an instrument that is working now at Gemini South. And this astronomer name is Joan Font Serra, who is a person from Spain. He was explaining us how this amazing instrument will provide exciting science in the following years to all the astronomical community. We talk a little bit about the diversity in the astronomical community and the importance of having a very well diverse environment in terms of people who contribute to the astronomy for human science. And also we talk a little bit about careers in astronomy, and John motivates students to be part of this amazing world of astronomy. So that's the summary of our previous session in Spanish a few hours ago from Chile. Thanks, Jamaica.
Bueno, gracias, Manuel. I'm so glad you can be here with us today, and we appreciate those insights from today's earlier show, and maybe we'll have some similar questions that we can follow up on today. So feel free to share with us as well, Manuel, throughout the show, sharing your insights.
Thank you very much.
So if you are new to Live from NOIRLab, we are going to start with a brief introduction to Gemini Observatory. Now, the International Gemini Observatory is actually one of 5 programs of NSF's NOIRLab, which is the preeminent U.S. National Center for Ground-Based Nighttime Optical and Infrared Astronomy. Gemini Observatory is composed of twin telescopes, and those twin telescopes are located in 2 places. One is located here on the Big Island of Hawaii on Mauna Kea at an altitude of just almost 14,000 feet. And that's a little over 4,000 meters. And Gemini South, which is where we're going to be talking about today, is actually located on north central Chile's Cerro Patron. So in this video, you can see how the dome is open. Gemini observes invisible and infrared light. Our 8-meter reflectors, which are a little over 26.5 feet, collect this light from mirrors that are actually coated with a special layer of protected silver rather than aluminum, which tends to be the traditional coating for large telescope. The mirror is made out of a large, these low expansion glass. It's about 20 centimeters thick. And here, as the video ends, you can see the vents are open, and this allows for the cold night air to flow through the observatory, which produces very stable images. So Gemini, with a telescope in each hemisphere, really allows us to be able to observe objects throughout the entire night sky. And there will be a link to this video and the recording in the show notes. Now, for our science highlight today is actually about today's topic, GHOST. GHOST is the Gemini High-Resolution Optical Spectrograph. Now, for some background, let's take a look at our latest CosmoView video. And let me just make sure my video is being seen. Rob, can you confirm that you can see my video?
I see video. I see the video. It's not playing yet, but I see it.
Confirmed. Thank you so much. Okay. Now, GHOST is going to revolutionize what we can learn about the universe. This new high-resolution spectrograph has finally been installed after 10 years of design and construction. Now it's at Gemini South, and this spectrograph, which spectrographs provide vital information in astronomy by analyzing the spectrum of light emitted by astronomical objects. This is really going to revolutionize how we can understand the first chemicals, the first stars and galaxies. Here you're seeing a spectra of its first light image, and we'll talk a little bit about that. Now that it's been commissioned, GHOST is actually going to measure the chemical composition, motion, and rotation of stars and galaxies, especially those first stars. Now, here to tell us more about GHOST is today's guest. Venu, please come on screen.
Hi, Jamaica.
Aloha, Venu. So here to tell us more about GHOST, that is Gemini South's newest science instrument, is Venu Kalari. Now, Venu is a NOIRLab scientist based at Gemini South, the Gemini South telescope in Chile. Venu's work includes overseeing the operations and commissioning of GHOST. Again, this is the Gemini High-Resolution Optical Spectrograph. Venu's research focuses on studying how stars form, particularly those stars in external galaxies. Welcome to the show, Venu.
Thank you, Jamaica.
Now, my first question, and many people may know this, that, astronomers love acronyms. Can you tell us if GHOST, if the name GHOST, the acronym came first, or if the name Gemini High-Resolution Optical Spectrograph was first? Which one? Because I love GHOST as the acronym for this.
Well, the acronym came after the name because initially we called it the Gemini High-Resolution Optical Spectrograph, which was just GHOST without the T. And and it is quite funny that you asked that because GHOST itself doesn't have any ghosts. So ghosts are features that you see on detector chips. So detector chips are basically when you take an image, the image falls on a sort of piece of hardware that captures the image by shifting the electrons inside that semiconductor. And sometimes, because if the image is really bright, you sort of see a halo around an object, and sometimes further away, sometimes closer by. And basically, GHOST doesn't have any of these ghosts. That's a test we did recently in July, early July, and we confirmed that it doesn't have any. So it's funny that it's called that, but we busted the ghost basically. So,
Wonderful. Well, I'm glad Ghost does not have any ghosts, as you explained, Venu. All right, so please feel free to share your screen and get us started. And tell us about this new instrument there at Gemini South.
okay, thank you. Just a second.
And while Venu is preparing to share his screen, I mean, just remind everyone in our YouTube and Facebook audiences to please share your comments and questions anytime in the chat. And I am jumping in the YouTube chat right now. All right, Venu, we are excited to learn about GHOST.
Thank you. Can I confirm that you can see my screen in full?
Confirmed, Venu.
Thank you, Jamaica. And thank you for this opportunity from NOIRLab to talk about the new instrument GHOST. So the first image really strikes me because it's such a beautiful image of the night sky as seen from the Chilean Andes. Now, I've been extremely lucky to have the opportunity to sit under such a night sky. And I've looked up at the stars and I've thought, oh, wow, could it be possible that we could know what each star is made of? And what if each star has a planet around it? Would we ever know? Would we ever find out? Is it still a little speck of shining light that's all we'll ever see? But I think it's not, because with instruments, especially instruments such as GHOST at Gemini, we can find out what these stars are made of, and we can find if they have planets around them. And I think this is how and why I want to talk about this particular instrument, and especially that's located at Gemini in the Chilean Andes, and how it can improve our understanding of the universe, so to speak. So before I dive into the actual nitty-gritty of how everything works, I want to take a step back and try and explain to our viewers, what is it we're seeing and why is it important to us? So all information we can glean from the universe reaches us in the form of electromagnetic radiation. So everything we can see, the sun, the moon, everything is some sort of electromagnetic radiation. And from this, we can deduce what we know about the universe. Now, this radiation is not pure white light. It's spread over a spectrum. And that's the components of the actual light itself, or the radiation itself. And by spectrum, I mean that because light can be considered as a wave. So if you measure the size of the wave from one end to another end, it sort of has a length. So the longest waves are probably radio waves, which we can't see by eye, and the shortest waves are gamma rays, which we also can't be seen by eye. And there's a huge span of length between them. But a very small fraction of that is visible light, the light that we can see, the colors of the rainbow, basically. And that visible light contains a lot of information about the elements in the universe that we can see, but also other artifacts that we will use from instruments such as GHOST to understand more about what we are actually seeing. So as I've explained, these objects, stars in particular, which are considered the building block of what we see in the universe, radiate light from the inner core. But they can also emit and absorb light. Now, what do I mean by this? So, say for example, you have a source of white light, like say the star in this image right here. If we see the star without any intervening gas, we could just see a pure spectrum of the rainbow. But that's generally not what we see when we look at spectra of stars or any part of the universe. We see sort of these little kinks, these little lines. And that a long time ago got people thinking, what are these lines? And in particular, one female astronomer, Henrietta Leavitt, they discovered that these lines tell us what elements that this light has passed through. This is because following quantum physics, there's discrete packets of energy where elements can absorb or radiate light. So if light of a particular wavelength, which translates to a particular energy, light of particular energy hits this element, it sort of absorbs and radiates, or absorbs or emits, depending on the energy it gets. And so each element has sort of a unique spectra, a unique line in the range of electromagnetic radiation. So from these lines, we can deduce what elements we see in the spectra we see. So they can be elements intervening between us, or elements that are emitting, which would be generally in regions of very high density where there's a lot of pressure, and then these elements emit light. So from this we can deduce, hey, what are we seeing and what's happening between. Now to go back to actually what Jamika was talking about Gemini Observatory in the very beginning. Gemini is part of NSF's NOIRLab and consists of 2 telescopes, one in the Northern Hemisphere in Mauna Kea, in Hawaii, around 4,000 meters, and the other one in Chile, on top of Cerro Pachon, which is where I work, and I've been very lucky to visit many times. And these 2 telescopes overall cover most of what we can see from the night sky. They're sort of like a telescope in space, but just with the atmosphere in between. And they're somewhat similar instruments. So if you want to observe an object and you don't have the ability to observe it from one telescope, you can see it from another part of the night sky. So I want to talk in particular about Gemini South, because that's where I work and that's where GHOST is situated. So over here, we have a picture of Gemini South with the vent gates open, as Jamika previously described. So this is done so that the air is stabilized. So when we take images, there's no turbulence in the air that can distort the quality of the images we see. Now, Gemini South is particularly huge. It has a primary mirror of 8 meters. So to give you a scale of that, here's a human being in between the mirror. So what happens when the light is gained from a telescope? The light enters the telescope, bounces off the primary mirror you see, and hits the secondary mirror, which you can see on the top of the baffles, the black box, so to speak. And then when it bounces off the secondary mirror, it goes and hits the instruments, which are located at the bottom of Gemini South. So you can see the instruments below the blue cladding, so to speak, inside the blue cladding, so to speak. This is where most Gemini South instruments are located, unless they're too heavy, which they can't, which is the case of GHOST, which they can't be located there. So I'll talk about that a bit later. So I hope the users can get a sort of a scale, a feel of how big the telescope is, and then also how remote it is. So this is a picture showing the Cerro Pachon, where Gemini is located. On the same scale, there's on a 50-meter scale, and that's a 5-kilometer scale. As you can see, it's just mountains all around. And through those mountains, right from sea level, comes GHOST. So it's a huge undertaking to transport a spectrograph, which contains components from all different parts of the world on top of this mountain. And we're very fortunate that we've been able to do that here. So moving forward, we would like to describe a little basic timeline of how GHOST came to be. So the picture of the telescope, the picture of the instrument, how did it all come to be here at this point in time? So in 2010, 2011, solicitations began to build such a spectrograph at Gemini South, and the contract was signed. Unfortunately, at 2013, there were some issues, and we had our Canadian partners step in to build the spectrograph in combination with our then Australian partners. In 2018, we first actually commissioned a unit of GHOST that sits on the telescope, and the whole commissioning was expected to happen in 2020. But lo and behold, the pandemic hit us, and we had to wait a further 2 years. But now we have a beautiful instrument which takes amazing pictures, which I will show you later on. And also to highlight the sort of collaborative effort, GHOST contains components built by very different companies in very different parts of the world. So it contains an own telescope unit that's built by, and a software and data pipeline that's built by Australians, but also the spectrograph itself is built by the National Research Council in Canada, and it's built on top of a Chilean mountain. So it's based on top of a Chilean mountain. So it's highlights the very collaborative nature of astronomy. So GHOST had its first light. So we first saw the first images coming from GHOST in this month, in July 2022. And as Jamaica has shown, they look very spectacular. And I will discuss a bit more why they look so spectacular. GHOST is also very similar to Maroon X at the north. So it sort of ties in with that very similar capabilities of Gemini North and Gemini South. So you can observe different parts of the sky with something very similar. So what about GHOST itself? Like what about the difficulties faced by the instrument team putting it together? What does it offer us, and how can it improve astronomy as a whole? So here's a picture that shows the instrument itself. So as I've told you, most of Gemini's instruments are placed right beneath the primary mirror, but high-resolution spectrograph in particular are notoriously known for being very large. So GHOST could not sit on top of, behind the primary mirror. So to overcome this, there was a very unique engineering concept in that we have an on-telescope unit, and then there's a fiber cable that goes right down to the bottom, to the dungeon, so we speak, of Gemini. And in there lies the spectrograph, which takes the science images. So what can actually GHOST do? So what does all this capability tie into? GHOST has two modes. There's is a standard resolution mode, and that can separate wavelengths up to 0.01 nanometers apart. So I'll come into this a bit later. Why is that so important? It can also observe very faint targets that can be captured by other space-based telescopes. And this is very important in this era, where if we observe something in space and we want to follow it up, GHOST is there to do that. And that's one of the capabilities of GHOST. In the high resolution mode, it can separate wavelengths. So if you imagine a spectrum, it can separate two different points in the spectrum, 0.05 nanometers apart. That's extremely small separations between two different orders of wavelength. And it can also identify wobbles of 10 meters per second. So these are all capabilities that maybe sound like jargon, but I would like to come later on to see how it ties into the whole picture of what GHOST can offer.
Venu,
yes.
Can I follow up here with something that you just touched on, and how it can GHOST will be able to work with and collaborate with other telescopes. I'd like to point out that I dropped in the YouTube chat the link to today's press release on GHOST. And there, Venu, we learned that GHOST will be able to provide some crucial follow-ups to to future surveys, such as the Vera Rubin Observatory, which is, of course, will be a program of NSS NOIRLab when fully constructed, which we're excited about. But also the Sky Mapper and Gaia. Gaia, I think I know I've definitely talked about Gaia in conjunction with other guests before, but I'm glad that you mentioned that GHOST will be able to provide support in collaboration with these other observatories and telescopes.
Well, thank you, Jamaica, for pointing that out. Yes, that's certainly one of the GHOST primary science cases. So GHOST itself is an Echelle spectrograph. So an Echelle spectrograph is slightly different to a standard spectrograph. It has different grooves or gratings that can separate light to much further separations than can normally be done. So these can range from, like as I told you about, to 0.05 nanometers to much further up. And that becomes very important to identify different elements in a spectrum or to identify planets in the spectrum itself. So here we see an example of an shell spectrograph, how the light bounces onto a grating, and then it bounces on the shell grating. It sort of separates the light further up. And then we also see an image of ghosts doing exactly the same thing, but in the lab with our engineers. And so once Ghost was built, it was put into the PA lab, the dungeon, usually the bottommost level of the Gemini. And that's, you can visualize that in the image I showed before over here. So that's where Ghost, the spectrograph, actually resides. Now there's an on-telescope component, and that's pictured up here. So this actually takes the light from the telescope itself and then feeds it via fiber to the spectrograph that we see below. So that relates to the pictograph I showed of Ghost right here. So there you can see the on-telescope unit, but you can also see someone opening up the on-telescope unit. And I'd like to give the opportunity to viewers to see, hey, what's inside of it? And then here, voila, we have the inside of the on-telescope unit of Ghost, so the category unit, as we like to call it here. So inside, Ghost has two IFUs. So IFUs are sort of like fiber lens slits that capture light, and then they send the light out into a little slit that you can see here. So there's two IFUs that can be visualized that are right in the middle of both sides of the middle in the image, and the light from that IFU is pictured as a green circle right there in that image, and then it's re-imaged into sort of a sequence that we can extract a spectrum from. So when you actually get everything put together in action, actually, there is the IFU as it looks on sky. And then you re-image it into a little slit. And then you actually see the final spectrograph, which can be seen here. And this looks suspiciously similar to our spectrum that we discussed upon in the very beginning. So this is just to tie it all in about the spectra at the very beginning, that we can learn about the universe and how does Ghost take spectra. So I hope the users have got a feel of what Ghost does to take such spectra and why the spectra are important. And now I would like to take the opportunity to talk particularly about Ghost itself. So why do we think Ghost is such a good instrument at Gemini? Is because Ghost can observe objects at very high resolution, and this is a capability that is not present in the southern hemisphere for an NOIRLab, and it can also observe objects that are very faint. So this is very important for following up objects which have been discovered, or special unique targets which have been discovered by other space telescopes such as Gaia, maybe even JWST, and also it can observe objects at very high precision. So why do we think the resolution is very important? So resolution, we can sort of imagine it as the smallest separable difference between two different points in the spectra. So on this figure here, you have a lower resolution spectrum in blue and a higher resolution spectrum in red. So if you were looking at low resolution spectrum, you would just see 4 different mountains or peaks. But if you were looking at a higher resolution spectrum, oh wow, you can see a lot more features. You can see many different lines, and then you can relate those lines, the wavelength of those lines, to what you would see a wavelength in a lab, and you can match the wavelengths and say, hey, I've seen that element in the lab at this particular wavelength. I know that that element exists because I've seen it in the spectrum of that particular wavelength, and voila, I know what element exists in that star. And so this is why you really need high resolution spectrographs, because they can separate many different chemical elements. And sometimes, especially in the visible part of the spectrum, there are many elements that are very bunched together that can only be separated by the highest resolution that's achievable. But it's also useful to measure the transits of planets. So that's something I'll talk about in the upcoming slides.
Venu?
Yes.
Can I pop in with a question from our YouTube audience?
Yes, of course.
Fantastic. Okay, so this question is from Alan Jackson. Alan says, HR spectrograms appear quite complex and abstract and data dense. Machine learning works very well with similar dense data. Will machine learning be productive in analyzing and interpreting ghost data as well?
Oh, thank you, Alan. That's a very pertinent question, I think. Machine learning would be very important in analyzing the data from ghosts, and certainly has been applied to other high-resolution spectrographs. In ghost, currently, we have no plan to use machine learning, and that is simply because of the way Gemini operates. So Gemini operates on a user basis. So users send in targets to observe which they think are unique, and there exists a panel of chosen scientists that assess the proposal. And then it's up to the user to reduce the data and analyze the data. So each reduction and analysis of, say, ghost spectrum would be dependent on the user, so there doesn't exist a machine learning or a data-driven algorithm to analyze the data. However, it is planned that there will be a large survey of spectra that will be taken by ghosts, following up on chemically peculiar and metal-poor stars. And I believe that team is planning to use some data-driven or machine learning approach to at least identify the lines in the spectra itself. So I hope that answers your question, Alan, and thank you for bringing it up.
Thank you so much, Venu. That was an excellent response.
Thanks, Jamika. Now, moving on. Oh, I seem to have. Yeah. So now that we've talked about resolution, the next important point that GHOST is specializes in is observing faint objects. So if you see two stars in space of equal brightness, say you see them at two different distances. So on the y-axis here, you assume there's distance, and you see two stars. Okay, they're the same equal brightness. Now, how would we see this in space? So if you put a telescope on Earth and we see the two same stars, nearest star is way brighter because it's closer, and the further away star is way fainter. It's fainter away. So you would think, oh, okay, why are the faint stars important? And it's because when we're looking back, we're looking farther in distance, we're also looking farther in time. We're looking at older stars because the light from those stars has taken that long to reach us. Now we're looking at much older stars, and it's those stars that turn out to be interesting for that reason, because they're older as well, and they can offer more unique insights into how the universe was a long time before, but also because much of the close universe has been well studied by much smaller telescopes or even earlier. So these are the stars, the more distant and more fainter stars are what we want to get, because those are the ones that haven't been studied yet, and you want to make a leap forward. So especially it becomes very pertinent because Gaia and the James Webb telescope will pick out very faint stars in space that are very unique and can offer us many unique insights into how the world around us works. And those are the stars we want to follow. So it's very timely that GHOST is present and that can observe very faint stars. So it can follow up, say, a star detected by the Gaia Space Telescope, which have sort of equal faintness limits as GHOST, or a star picked up by James Webb telescope, but maybe a much brighter one than the faintness limit of James Webb, but it can observe it in the optical, which James Webb can't do. So GHOST offers these unique capabilities that don't exist for many of the other NOIRLab facilities. And finally, why is the precision important? So the precision becomes very pertinent when we want to identify planets around stars. So if you take one step back, to understand how we detect planets around stars, we need to assume that there's a star and it has a planet around it. Now, gravity doesn't just attract the planet towards the star, it sort of moves the planet and the star and puts a equal center of mass depending on the mass of the two objects. So the star moves around this circle, and so does the planet. And depending on if the star is really small in mass, it's basically the star itself. But if the star is slightly big in the planet is slightly big in mass, the star as well has a circle around which it moves. And when the star moves in one particular direction, if we say it in our line of sight, you can see it move to one direction and to another direction. And as you can see in this pictograph here, you could see a slight shift in the wavelength of particular lines in the star. So this is not caused due to anything in the elemental abundance or anything, it's just caused due to the star's motion. And if our telescope and our spectrograph is precise enough to capture the movement of these lines, we can certainly identify planets around these stars. And this is very important, and it was the first used method to identify a planet around a star, and it's certainly one of that picks out the most planets around stars. So it's very good that GHOST can follow up at much higher precisions than available before for NOIRLab facilities. So now I've talked about how we got GHOST up at Gemini, what was the timeline of GHOST, and why is it so important? Well, we tried to put GHOST into action, and the very first thing we encountered was a snowstorm. So when we were sitting up at the telescope, it was snowing all around, and we couldn't take any data, and we were defeated. But at least we had some very pretty images. So there's nothing important about this slide. I just want to show you images of the snow at Gemini. But finally, we got some data, and this is how the telescope works. So I'll just take a moment aside to tell you how the operations work. So once we get the data is fed into a computer, and that computer pops up the images that we see directly on screen. So you have like different screens, one showing the telescope sensors, like say the temperature, and then one showing the weather sensors, saying the wind, the humidity, and one showing images, and ones that are used to operate the telescope and the instrument itself. So once we look at the images, we can see it live when we get the data, and this is basically showing some of the first images being taken by GHOST, and the engineers and the instrument scientists celebrating taking those images. And moving on, I would like to show, hey, these are how the images look like. So there's two images. One is from the blue end of the spectrum taken by GHOST, and one is the red end of the spectrum. So GHOST splits its light into two different detectors, one's for blue and one's for red. This is due to the sensitivity achieved by each one. And each line that you can see is a spectrum of some particular wavelength. So if you imagine back to the very initial slide I showed with the spectrum, each line here is one of those spectra. So you can imagine the distinction in wavelength. So each line covers around 30 to 50 nanometers in wavelength. And together they cover almost the completely visible part of the spectrum. And this is a much more beautiful reduced part of the data, which I think Jamika showed, which is of the chemically peculiar star HD 222925. So here we have the spectrum, but colored according to the wavelength of light we would see it. So you have blue light, which is the shortest wavelength we see, going right up the way to the red and the violet light. So here is an actual example of the final spectrum that astronomers would use for science. So each line in that image I showed before is sort of cut. If you can imagine like taking just a small cut along that line, that would show up as one particular peak here. And those peaks are all joined together to make the beautiful spectra we see. So here's an example of the chemically peculiar star that when you cut it along the spectrum, that's how it looks like. And here is an example, I believe, of the sun. So now we've seen that GHOST is in action and what the spectra look like, and the colors we can see of the visible wavelength spectrum. What are the exciting science things that we expect to see from GHOST?
Venu?
So, yeah.
Can I jump in here and follow up on as a bit of detail on the spectrums that you just showed?
Yes.
Okay, so in the press release that I've put in the chat, that link, one of the views of the spectrum we get is actually goes through and points out the different lines.
Yes.
The signatures that we can actually see in the lines, which include the hydrogen beta lines, hydrogen gamma, calcium lines. Do you have that spectrum to show us and maybe give us a bit of detail?
I'm sorry, I don't have the spectrum on hand to show.
No worries, I have it. Can I share my screen and maybe you give us a little bit? Okay, share us a little bit about this. Oh, yes, okay. Okay, let me pull this up. I believe it's this one. Yes. Okay, are you able to see my screen, Venu?
I can.
Okay, can you tell us a little bit about what we're seeing? We have some text here guiding us, but give us a little bit of insight here.
Could I ask to expand the image, please? Is that possible?
I don't know that I can do that, but you know what? Let me stop my share and I will drop the link into the chat so that you can click on it and have it on your screen, because I think one of the things that when I first came into astronomy, I learned how important spectroscopy was, and getting a spectrum and learning how to read those lines, emission spectra, absorption spectra, and learning how to read those lines and see what the chemical signatures are and what it's telling us. Venu, I think it's one of the key vital things that always is exciting to me. Yes. Okay. All right. Tell us what we're seeing here, Venu.
So from here, as I spoke about, you see the very blue end of the spectrum, so around 350 nanometers. So that's the very limit to which the human eye can see, or slightly beyond the limit, I would say, to which the human eye can see. And that part of the spectrum is really metal dense, especially for stars such as HD 2295. So these are, by metals, astronomers are slightly old school in that metals mean any element that is heavier than hydrogen and helium. Now, I think a discerning viewer will ask, why did this come about? It's because when you go right way back to the Big Bang, almost everything that we had in the universe was hydrogen and helium. And we had nothing heavier than that. We had hydrogen, small amount of helium, and a very, very small trace amount of lithium. So all these metals that we see were formed inside the cores of supernovae or other dying stars, such as neutron star mergers. And looking at these spectra, you can understand how these metals were formed by counting the density, counting the amount in these particular stars, and trying to date the star. So that's where the metal-rich region of such a star comes into play. So there are two processes which we think that these metals are formed. One is the rapid process, which is called the R process, and one is the slow process, the S process. So both form in very different mechanisms. And the rapid process happens when neutrons are captured rapidly. And so a light element such as helium or hydrogen is rapidly captures neutrons, say in a neutron-neutron star merger. When it explodes, they rapidly capture the neutrons, and then they grow and they become elements such as gold and the gold or the iron and so on. And the slow process is when supernovae explode and they release what they have been nuclearly fusing inside their core. So this is where the metal-rich region comes into play. And then the other lines are calcium, H and K lines. So these are very distinctive of stars such as the sun, and they can help to identify these stars. So stars are not all made alike. You have low mass, and the most discerning factor of a star is its mass. So you have the very low mass stars, which can be slightly more massive than Jupiter. And then you have really massive behemoths that can be like 150 times or even greater than the mass of the sun. So to identify particular stars, you look for particular lines in the spectra. And then you can also type, sometimes we call them to type the star. So the calcium H and K lines can be very useful to type, especially a solar mass type star. And the hydrogen gamma, hydrogen beta, and hydrogen alpha are transitions that are seen in the hydrogen Balmer series. So when electrons of a particular energy are present in the star's atmosphere, and when it absorbs that energy when the light passes through it. So these transitions help us identify the energy, but also what's in the star's atmosphere, and you can say how much hydrogen was there in it. So all these features tell us something unique about the stellar spectrum itself. The atmospheric feature is slightly more mundane in that it's just a feature that you can see in the night sky. So if you look down in space, you will see the atmospheric feature. It's basically a combination of water vapor, ozone, oxygen, all these elements that we need as human beings, but as astronomers, we could live without.
Got it. Thank you.
I hope that covers some of the features that were described here.
Oh, it does. It does. Thank you so much for that, Venu. I appreciate that. And we do have another question from the YouTube audience, but I'll come back in a few minutes with that, Venu. Thank you.
I'm going to stop sharing for a second just so I can share my actual Zoom screen. Yeah. So that's the spectra, and this is the beautiful spectra we get as an example. And this is another example. But to many of the users who've been interested in what kind of science we can do with ghosts. And one of the very curious cases, which sadly we don't have like an example I can show here, is galactic archaeology. So going back to what I talked about, seeing elements in the spectra, so if you look at spectra of really old, faint stars in the very distant spots of the galaxies, you can identify sort of how old these stars are based on their chemical elements and the chemistry of these stars. And you can sort of like say, hey, I've discovered one of the oldest stars in our galaxy, which is around 10 million years. And I like to think of them as the Indiana Jones of astronomy. So there's something which we're especially keen on with ghosts, that we identify really old metal power stars. And this is an example spectrum of HD 22925. So this is sort of the spectra which Jamaica showed us earlier, but in a 1D format. So you can see the lines, and this is the lines that we see, and they're identified. So you can identify your very unique elements because it's a very chemically particular star, particularly in the blue part of the spectrum, which is shown in the top, the heavy elements. This is iron, europium, yttrium, zirconium. So all these really cool elements that you can see in this star. And also I wanted to take the opportunity to highlight the impact of resolution. So this is a picture of a ghost spectrograph in the bottom, but on the top, you can see the spectra taken by a high resolution spectrograph in black, but also a low resolution spectrograph in gray. And sort of, if you look at the gray lines, you sort of like lose a lot of lines that you would have otherwise identified. So it becomes very important to identify a lot of chemical elements. You need high resolution spectra. Another science case which I would like to highlight, which is sort of at the very other end of the spectrum, or the other end, so to speak, is quasars. So quasars are very highly luminous objects in the early universe, and they have massive black holes in the center which sort of blow out the energy from them. So when you look at a quasar, you generally see a lot of lines. And these lines are not lines generated from the quasar necessarily. They're actually generated from the intervening clouds and dust between us and the quasar itself. Because quasars are so energetic, but also they're located so far back in the early universe that when their light reaches, it passes through so many clouds of dust and gas. And sort of all the lines are shown were especially lines of neutral hydrogen, which can't be identified by many other means. And quasars are one of the very unique means that we can identify these lines. So by looking at this forest of lines, so to speak, which happens at the transition of Lyman alpha, which is much further in wavelength than GHOST can see, but we can see because if we read the lines redshifted, you can see all these clouds, the intervening matter between us and the clouds, or us and the quasar, and of these clouds, and you can identify, hey, this cloud has neutral hydrogen and it's located here. Another particular science case I would like to highlight as well from GHOST that would be very considerably studied would be, say, emission lines, and in particular, say here, a planetary nebula. So many people might have seen from JWST these pretty pictures of planetary nebula, which are basically low mass stars that have died and they've cast out their atmospheres in these beautiful, spectacular ejecta. Now, when they cast out these ejecta, they can form very dense layers, and these densities and temperatures are what gives rise, when light passes through them, what gives rise to emission lines. So these, in contrary to normal absorption lines where light is absorbed by the element, these are emission lines. So these lines are made, and you can see a lot of hydrogen emission lines in the bracket series that you can see in this nebula, the Stingray Nebula. And so you can identify different lines, and you can identify a small wavelength space in between them. So I think I have taken the opportunity to identify, to show different types of spectra that can be studied with GHOST to different objects. So when will we actually see more science, and when will we actually see a lot of what GHOST will output? Well, we hope to be taking data regularly from late 2022 to early 2023. And we believe that there will be a lot of exciting science to come, particularly from the NOIRLab and Gemini community. There is a lot of keen interest to use GHOST for a variety of science cases. And in some of the cases, I've only demonstrated only a small fraction of the science cases which GHOST can be used for. And finally, I would like to take the opportunity to thank our team, without which none of this would have been possible. So we have an amazing team which comes from all over the world, from Australia, from Canada, and also especially our Gemini team in Chile, who have worked through very challenging conditions, especially weather conditions, to take data and to make sure GHOST is functional and operational at GHOST at Gemini. So yeah, I think credit all goes to them, and without them, this talk would never have been possible. So I'll leave the recap slide up there, and just to summarize, that say GHOST is our high-resolution faint object spectrograph based at Gemini South, and we hope to have operations in science from late 2022, early 2023. And some of the science cases I've shown, and there's more science cases, and in particular galactic archaeology, finding exoplanets around stars, and especially to follow up targets from space telescopes such as Gaia and JWST. So thank you, Jamika and Manuel and Rob for this opportunity. And yeah, I'm ready to take any further questions.
Thank you so much, Venu, for this fantastic presentation, introduction to GHOST. All right, so we have two more questions from the YouTube audience. But before we get there, I'd first like to get your response to this. Again, in the press release on GHOST that came out, that was released today, we have a quote from the Gemini director, Jennifer Lotz, who says, quote, "This is an exciting milestone for astronomers around the world who rely on Gemini South to study the universe from this exceptional vantage point in Chile." She continues on, "Once this next generation instrument is commissioned, GHOST will be an essential component of the astronomer's toolbox," end quote. Okay, so how can astronomers reach out to use this tool? What is the process that astronomers would have to go through to gain access to using GHOST?
So at Gemini, we invite proposals to observe with GHOST. I think the call will go out in late September to observe science with GHOST from any of our partner communities. So that includes Argentina, Brazil, Chile, Korea, Canada, and the US. Now, the US also offers open skies time, which means that anyone from anywhere in the world, if they have a good science case, can write a proposal and submit it, and we will take that data for them. We want the best science to be done with GHOST, and that's why we have this open skies policy for the US allocation of time for GHOST. So if you think you have a convincing proposal that does great science, please, by all means, we would like to receive that.
That is good to hear, Venu. It seems to me that that is one of the ways that NOIRLab is helping to broaden our impact, broaden access to data, to instrumentation, to world-class observatories through maybe this open skies policy.
Yes, that's one of our aims. We want the best science to be done, and we do not want any hindrance to that. So I think this is one of the best policies that we can offer our astronomers around the world.
Absolutely, Venu. Absolutely. That is exciting to hear. All right, so we'll follow up with our last few questions from the YouTube audience. And again, I want to thank everyone who has been watching, who's joined us on Facebook Live, YouTube Live. Whether you made a comment or not, we can see you there. Okay, our last two questions are from Alan Jackson. So first, a comment. He says, so you don't need to observe the orbital plane of the subject in order to detect exoplanets. So that's the question. Thinking about exoplanets, is there a need to observe the orbital plane of the subject in order to see these planets outside of our solar system?
Yes, so you don't exactly need to observe them in the orbital plane, but you need it to discern the very exact mass of the object. So without knowing the inclination angle, so say if you have a planet or revolving around a star, and it goes like that, like say, and you're observing it like this, if you observe it straight on, you can see the star wobble really well. If you see it perpendicular, you can't see it. But if it's more stars would be inclined, they're not going to be either face on or inclined like that way. So most stars are going to be inclined. So without that, if you don't have the inclination angle, you can't get the mass. But unless it's perpendicular to you, you can't. Only in that case you can't see it, but otherwise it doesn't matter. So it only matters while getting the mass of the star. So you can't get very precise mass estimates.
Okay, thank you, Alan. Very good, insightful question there. And then one more, Venu, as we are in our final 2 minutes. Again from Alan, he says, so where would a team, obtain an HR spectrogram data to train a machine learning model? So, any suggestions?
So we offer all data that's taken at Gemini to the public within 6 months. So after 6 months of your data is being taken, it becomes public. So in a while, you get an archive of data which you can train machine learning models from. There are other telescopes which do have the same policies and do offer archives, publicly available archives and publicly available data sets that you can use machine learning models on.
Oh, that's exciting. Okay, so training a machine learning model, that is just out of this world that we can actually do that right now, Venu, with this amazing technology. Where can we find eventually this archived data?
So this data set should exist in the Gemini archive, which is, I think, I don't know the exact URL, but I think if you do a Google search for Gemini archive, it should turn up. I think it's just something like gemini.edu/archive, archive form, or something of that nature. So it's very easily accessible, and after 6 months after the data is taken, it usually becomes public, unless there's a very particular reason where it shouldn't be.
Fantastic, Venu. I just found it, and I will add that to the I'll add that here in the chat, and it will also be in the show notes once the recording is posted. Well, I would invite everyone who's with us today, Manuel and Rob, to come on screen in this last 1 minute to thank our guest, Venu Kalari, for being here with us today, giving us insight on this fantastic new high-resolution optical spectrograph GHOST at Gemini South. So for my last question, and I would love to get this response from Manuel and from Venu. Manuel, what do you see as the benefit of doing these kind of special edition shows where we not only presented in Spanish, but in English as well? What is the benefit that you see to that as we're thinking about making things more accessible to those who may normally not be able to join us?
Yeah, well, the vantage point of being in a virtual modality allow us to share this amazing science and technologies from NOIRLab with the public from everywhere in the world, and of course for those who cannot be in an all live session. When we used to do these all live sessions in Hilo, Hawaii, or in Tucson, Arizona, or in La Serena, Chile. This gives us a huge opportunity to share the wonders of NOIRLab with all the public all around the world.
Fantastic. Yes, I totally agree. Venu, same for you. Now, you are living down in Chile. So what is it like for you to be able to bridge these two worlds?
I think it's amazing. I think it's just the nature of how astronomy is done. And I think I wish the world was a more collaborative place where you have people from different parts of the world coming together for a common purpose and a common good, and joined by their desire to understand more about the universe. So I think it's great that we can spread that message in 2 languages. I wish in the future maybe we have many more languages to reach out a wider audience. But yeah, it's amazing. It's amazing to be given this opportunity. It's amazing to be here to do so.
Well, we certainly appreciate you for joining us, and I am grateful for the opportunity to do this special edition with you, Manuel, to do the English follow-up to your Spanish special, and a big mahalo nui loa to Rob, an amazing colleague, fantastic technical director, and moderator as well. Rob, would you like to share anything with us just in general about today's show, but in particular about the benefits of having a session like this in English and in Spanish, or in other languages as well?
I just think this is great. I was happy to learn about GHOST myself, since I didn't know as much about it. I've know more about Maroon X than GHOST, since I did a podcast on Maroon X, and maybe I'll have to get Venu on a podcast episode here about GHOST coming up soon, so we can get that to our podcast audience as well.
Absolutely. I did not think about our podcast. Thank you so much, Rob. Yes, our podcast on 365 Days of Astronomy. Rob does a fantastic job hosting our podcast. And yes, maybe we can hear Rob and Venu in an upcoming episode. With that being said, I'd like to thank everyone for joining us here today. Our special guest, Venu Kalari, talking to us about the GHOST Gemini High-Resolution Optical Spectrograph, which is now on at Gemini South. Also, we had our colleague from Chile, Manuel Paredes, who earlier today hosted the Spanish version of this show. And again, of course, can't do it without Robert Sparks. Thank you all who were in our live audience today on Facebook and YouTube. And we look forward to seeing you next month on the next Live from NOIRLab. Aloha and mahalo.